Okay, so for today's lecture, we'll be doing section 1.3 in our course, Matrices and Matrix Operations. So we have seen some matrices before when we converted a linear system of equations to augmented matrix. So we formally discussed what a matrix is, and we work on the operations for matrices or between matrices. So a matrix is a rectangular array of numbers. So the numbers in the array are called entries in the matrix. Okay, so for example, these are all matrices. So in here you have an array of numbers with 1, 2 rows, and then there are 3 columns. Okay, in this example, you have 4 rows and then 4 columns. Okay, and then in this particular example, you have single column, okay, with 4 entries, and then in here you have a single row with 4 entries. Okay, so these are all examples of matrices. Now, if a matrix has m rows and n columns, we say that the matrix has size m by n written m cross n. So the first entry here will be the number of rows, and then the second entry here will be the number of columns. So m by n. Okay? A matrix with only one row is called a row vector. Okay? And a matrix with only one column is called a column vector. So if we go back to this example, this guy here, it's a column vector because it has only one column. And then this guy here, it's a row vector because it has only one row. Okay? Next, a matrix is denoted by uppercase letters, and the entries are denoted by lowercase letters. Of course, if you are talking about general form of matrices, the entries are not necessarily numbers, so we will denote the entries by lowercase letters. And then for the name of the matrix, if you want to give a name to the matrix, we denote it by uppercase letters. Okay? So for example, here is an m by n matrix in the general form. So we have the name of the matrix as capital A. It's an uppercase letters. And then we have these square brackets and then the letters inside. Okay? With which are the entries of the matrix. And notice that we are using single letter A but with 2 subscripts. Okay? Why are we using this? Because here the subscripts, okay, tell us which location the entry can be found. For example, here you have A11, the subscript 1. The first subscript 1 tells you that it is in the first row, and the second subscript 1 tells you that it is in the first column. Okay? For example, in this entry here, you have A to N. So the first subscript 2 tells you that it is in the second row. And then the second subscript N tells you that it's on the nth column. Okay, so this is the usual notation we were using when we look at the augmented matrix. Okay? Now, by the symbol Aij, we mean the entry at row I and column J, just like what I discussed earlier. Okay? So other notations that can be used. So you have your Aij, so just small bracket, small square bracket, and label Aij. And then the subscript of this bracket is m by n. It tells you the size of the matrix. So the number of rows and number of columns. Or simply, you just write it Aij if you are sure of what you are sure of the size of the matrix you are talking about. Okay? Or possibly if you are not interested with the size of the matrix. Okay? So you can just simply write it this way. Or just write capital letter by naming it. So, if A is a matrix, okay, capital A, the name of the matrix, then we can also have this symbol, but this means we are looking at the entry, okay, the entry, this time the entry of the matrix at the ij location. So this symbol here also denotes the entry aij. Okay, so look at the difference. So in here you have this notation, and then the outside you have m by n. So it tells you the size of the matrix. On the other hand, if you have something like this, it tells you the actual entry, small a I j. Okay? Now, if a matrix is a row or column vector, we use bold-faced lowercase letters. Okay? The entries will have one subscript instead. So for example, these two guys here. Okay? So here you have a row vector. Row vector, we use boldface A to denote this vector. And then the entries are A1, A2 until AN. So only one subscript because there's only one row anyway. So you are just looking at which entry in the row. Okay? And similarly here, you have a column vector. So we use boldface small letter B. And then the entries are B1, B2 until BM. Okay? So same explanation, we only use one subscript because it will only tell you which entry in the column. Okay? So we have those notations. Okay. Questions so far? Now, if a matrix has n rows and n columns, okay, same number of rows and columns, okay, it is called a square matrix. And we have this notation, of course, A11, A12, A1 until A1n, blah, blah, blah. You have AN1, AN2 until ANN. So this is a square matrix. And a lot of times we'll be dealing with square matrices. Okay? Now, for the square matrix A, okay, the entries A11, A22 until ANN are said to be in the main diagonal. Okay? So, if you are going to look at these entries here, okay, these are the entries in the main diagonal. And we are naming these particular entries because we will be considering them later. Okay? And there's a special usage of the entries in that in the main diagonal. Okay? Now, let us look at operations on matrices. First, we have this relation. Two matrices are equal if they have the same size and their corresponding entries are equal. Okay, so first relation. Two matrices are equal if they have the same size and their corresponding entries are equal. So for instance, let's have this matrix A with labeling A11, A12, etc. until A1n, and then the last row here you have AM1, AM2, etc., AMN. So meaning A has size m by n. Okay? Size m by n. And then let us look at capital B with matrix with entries B11, B12 until B1n tilde, take note of that tilde, etc. And then you have your Bm tilde 1, Bm tilde 2, until you have Bm tilde n tilde. So there's a line or a tilde above letters N and M. Okay? So we say that A and B are equal if M is equal to M tilde, so the same number of rows, and then N equals N tilde, same number of columns, so same size. Okay? And furthermore, N3-wise, okay, N3-wise, they are the same, meaning the Aij must be equal to Bij for all I and for all j. So N3-wise, so A11 must be equal to B11, A12 must be equal to B12, etc. Okay? So equal entries. So same size and equal entries. So that's when we say the two matrices are equal. Okay? Now, find the values of x and y so that the following matrices are equal. So for example, here you have x plus y, and then 2, then negative 1, and then x minus 2y. And then here you have b, negative 1, 2, negative 1, 3. So notice, this entry here is already the same with this entry. And then this entry here is already the same in this entry. So what we want to have so that A and B are equal is that your x plus y must be equal to negative 1 and x minus 2y must be equal to positive 3. Okay? So let's work on this. Here you have your x plus y, okay, equals negative 1. And then the other guy, you have x minus 2y must be equal to positive 3. Okay, so you have this system and you can solve this using any method okay. Substitution or elimination would be easy to use, since this is just two equations in two unknowns. So let us label the equations 1 and 2. So what we can do is to subtract equation 1 or subtract equation 2 from equation 1. So you have this minus this. So what do we get? So x minus x will be eliminated. And then here you have y minus negative 2y. Okay? Y minus negative 2y, we will get 3y. So y minus negative 2y will get 3y, and then in here equals, you have negative 1 minus 3, that's negative 2. Okay? And therefore, your y will be equal to negative 2 over 3. So now, you have a value for y. We look at any of the equations. We substitute y with any of the equation here. So you have your y, and then let us use equation 1. Okay, so sub in equation 1, we'll get x, plus y, which is negative 2/3, equals negative 1. Or that we have x equals negative 1 minus negative 2/3. So that becomes plus 2/3. And from there, what do we get? Negative 1/3. Correct? Negative 1/3. And yep, those are the values that we need so that the two matrices are equal. You can check it. Look at this. you have x plus y. So x plus y, it's negative 1/3 plus negative 2/3. That's negative 1. So you have this guy here. Whereas the other guy, you have x minus 2y. So minus 2y, you will have minus 2 times negative 2/3. That's 4/3. So positive 4/3. So minus minus 1/3 plus 4/3. What do we get? What do we get from? I have an error in this part. I apologize. So you have negative 1 in here, minus 3. This should be negative 4, right? That should be negative 4. So I apologize to that part. Should be negative 4. And then for the 4, we will have negative 4/3 here. Okay? And of course, since we changed this, we will have to change this part here. So this is negative 4/3. This is negative 4/3. And what will this be? So 4/3 minus 1. This is positive 1/3. So positive 1/3. Okay, so that should be the values of x and y. So I apologize for the error in here. And then you can still check x plus y. So you have 1/3 minus 4/3. That's negative 3/3, or that is equal to negative 1. And then in here, you have x minus 2y. So 1/3 minus 2 times negative 4/3. So 2 times negative 4/3, that's negative 8/3. But there's a minus here. So it becomes plus 8 over 3. So 1/3 plus 8 over 3, that's 9 over 3, and that's equal to positive 3. Okay? So question so far. So again, the main point here, two matrices are equal if entry-wise are equal. Okay? If entry-wise are equal. So question for this part. Okay? Okay. So let us look at operations on matrices. So we just have your first relation, equality of matrices. And I think that's the only relation we'll be talking about when talking about matrices. Now, operations. So we define sum, difference, and what we call scalar multiples of matrices. So let us consider this matrix, or these matrices A and B, okay? And we assume that they have the same sizes. Okay? Let A and B be matrices of the same size. So you can only add, subtract, you can only add and subtract if you have a matrix of, if you have matrices of the same sizes. For scalar multiples, it can be anything, because we will only use one matrix in scalar multiple. But if you are adding and subtracting, you must have the same size for the matrices that you are adding or subtracting. Okay? And if you are going to combine scalar multiplication with addition and subtraction, then the matrix obtained after doing scalar multiplication must be the same size as the other matrix. Okay? So A and B, matrices of the same size. Then, the sum A plus B. Okay? So this is a new matrix. Let us label it with capital C. And the entries are written Cij. Okay? And this Cij is equal to Aij plus Bij. So what does this mean? You add entry-wise. Okay? You add entry-wise. Okay? And then for the difference, A minus B, this is a new matrix, capital C, where the entries Cij is equal to Aij minus Bij. So you subtract entry-wise. So addition and subtraction, entry-wise. Addition and subtraction. Okay? Now, if R is a scalar, okay? Scalar, it's just a number. Scalar is just a term we use to denote a number, a real number, or in other areas, any number, complex number, possibly. Okay? So a scalar, then the scalar multiple Ra. So this is how we're going to write it. So scalar multiple Ra of A, this is the matrix Cij, okay, Cij with entries Cij equals Raij. So meaning you multiply your scalar to every entry in the matrix A. Okay? So again, if you add two matrices, you add entry-wise. If you subtract matrices, you subtract entry-wise. If you do scalar multiplication, you multiply the scalar to every entry of the matrix. Okay? Question. Let us look at this example. So here you have 2a minus b. So you have a scalar multiplication 2a here, and then you subtract b from 2a. And notice matrices A and B have two columns, two rows and three columns. Okay, so 2 rows and 3 columns. So you can do addition or subtraction in here. So let us do this step by step, just for illustration. So you have your 2a, okay, and then your 2. Let me write the matrix. So 2 times this matrix here, 1, 3, negative 1, and then 5, 2, positive 3. Okay? So this means you multiply these 2 here to each of the entry in this matrix. So you will have 2 times 1 in the first entry, that's 2. Okay? And then 2 times 3, this becomes 6. And then 2 times negative 1, this is negative 2. 2 times 5, that's 10. And then 2 times 2, that's 4. And then 2 times 3, that's 6. Okay? So this is your 2a. Now, if we do now 2a minus b, okay? 2a minus b. So let us copy the 2a in here. So again, I'll do this step by step. So 2, 6, negative 2, 10, 10, 4, 6, and then minus bracket negative 1, 2, 1, 2, 3, negative 3. Okay? And then we do the subtraction. So entry-wise subtraction, you have 2 minus negative 1. So let me write that. 2 minus negative 1. This is your first entry. Here you have 6 minus 2. And then you have 6 minus 2. Then here you have minus 2 minus 1. So you have negative 2 minus 1. Here you have 10 minus 2. So 10 minus 2. And then you have 4 minus 3. 4 minus 3. And lastly, you have 6 minus negative 3. 6 minus negative 3. Okay? And then you just simplify everything here to obtain, so 2 minus negative 1, that's positive 3. 6 minus 2, that's 4. Minus 2 minus 1, that's minus 3. 10 minus 2, that's 8. 4 minus 3, that's 1. 6 minus negative 3, that's positive 9. So this is the matrix 2a minus b. So entry-wise subtraction. And then here you have scalar multiplication. So you multiply scalar 2 to each and every entry in the matrix. Question so far? Okay. Another example here, you have the same matrix. Okay, you have the same matrices. And you now have a plus 3b. So let us start with the 3b. So again, I'm doing everything in detail for now, but you can combine them immediately. You can have your solution, combined solution for your answers. So first, you have your 3b. So you have 3 times negative 1, 2, 1, 2, 3, negative 3. So we have what? So negative 3 times, so 3 times negative 1, that's negative 3. 3 times 2, that's 6. 3 times 1, that's 3. 3 times 2, that's 6. In this part, 3 times 3, that's 9. 3 times negative 3, that's negative 9. Okay? And then a plus 3b. So we copy a. You have 1, 3 negative 1, 5, 2, 3. Okay? And then plus the 3b, you have negative 3, 6, positive 3, 6, 9, negative 9. 6, 9, negative 9. Okay? And again, for in detail, you have 1 plus negative 3. So 1 plus negative 3. Then 3 plus 6. And then negative 1 plus 3. And then 5 plus 6. 5 plus 6. And then 2 plus 9. And then 3 plus negative 9. Okay? And then you do the addition inside. You will have negative 2 here. And then here you have 9. Here you have positive 2. Here 11. Here another 11. Okay? Another 11. And then here you have negative 6. So this is the matrix A plus 3B. Okay? Now, if you're going to do your solution, and for us in the next solutions, you can start with this immediately. So you have your A, and then the 3B, you input this guy here, or you input this guy here to this part. Okay? So in your solution, you can have your A plus 3B, and then you input it here. And then on the next line, you can do the 3B, okay? And then you can add, etc. So you don't have to separate the 3B in the computation. That's what I am saying. Okay? You can just have A plus 3B immediately. question. Okay. Next, we call 2a minus b and a plus 3b linear combinations of a and b. Okay? So, linear combinations of a and b. And in general, we have the following. Suppose you have A1, A2 until AR, capital letters A. These are matrices of the same size. Okay? And we let C1, C2 until CR be scalars, meaning they are just numbers. Then, you have this sum here, C1, A1 plus C2, A2 plus until CR, AR. That sum is called linear combination of A1, A2 until AR. And C1, C2 until CR, so these numbers, after writing it like this, are called coefficients. Okay? So C1 is a coefficient of A1, C2 is a coefficient of A2, etc. CR is a coefficient of AR. Okay? Now, let us talk about products of two matrices. And please listen very carefully because multiplication of two matrices is not as easy as the addition, subtraction, and scalar multiplication. Okay? So, let A, take note of this, let A be an M by K matrix and B be a K by N matrix. So, different sizes. Possibly the same size if they are square, but the more general is that the number of columns of A must be the same as the number of rows of B. Okay, so M by K, K by N. And then you can multiply the matrix AB. In this form, take note, A is on the left factor, B is on the right factor. Okay? So, the product AB, this is the matrix Cij with size M by M, take note of that size, such that Cij is equal to A1, AI1, B1j plus AI2, B2j plus until AIK, BKJ. Okay? Okay? Let us illustrate this. First, sizes. So you have the size of A, it's M by K. And then you multiply it to B. Okay? You have K by N. So let me remind, A is a left factor in the multiplication and B is a right factor in the multiplication. Oops, factor. And you cannot interchange them. It's not always interchangeable. So if you multiply AB, the K here, okay, the K here must be side by side. So if you multiply them, the size will be M by N. That's the first. Okay? So, size of A, it's M by K. M rows, K columns. Size of B, it's K by N. K rows, N columns. You multiply them, you will have a new matrix of size m by n. M rows and columns. Okay? Now, how about the actual multiplication? How about the actual multiplication? So say this is your A. This is your A. You have your A I1, A I2, okay? And then you have your A I K, okay? So this is row I. This is here. This is your row I. Take note of that. And then you have your matrix B in here. You look at B, okay? This is your matrix B. So this is your B, 1J, B, 2J, until you have B, K, J. Okay? So this means this is your column J. Column J. Okay? So this row I on the left multiplied to column J of the right factor, it will only give you the Cij. Cij. Okay? So entry. So this is your capital C. This guy here. So this guy here, it's just the entry on ij or at ij. Entry at ij. So that's a single entry. You are multiplying a bunch of numbers. Okay? I1 times B 1J, and then AI2 B2J, and then you have AIK BKJ. Okay? You are going to multiply that pair, those pairs, and then you will add them. It will only give you one entry. Okay? And for more emphasis in here, what you're going to multiply. So you have this guy here, AI1 will be multiplied to be 1J. And then this A12 will be multiplied to B2J. And then this AIK, so go and work on the multiplication. You will just do those pairings in the multiplication. And then you will add all the sums. So that's what your Cij is. AI1 times B1J plus AI2 plus B2J plus until you have AIK here plus times BKJ. So once you have that, you will get the entry Cij in the other matrix. Okay? Question? Okay? Let us work on actual examples. So you have here A matrix A, and then matrix M. And notice, A has size 2 rows, 3 columns. So this is 2 by 3, 2 by 3, while the matrix M has size what? 1, 2, 3, 3 rows, 2 columns. Okay? 3 rows, 2 columns. Okay? So this is what we only need to check. This guy here must be the same as this guy. Okay? It doesn't matter if this guy and this guy are the same or not. Okay? It just so happened that for these matrices, this guy and this guy are the same. Okay? But they can be different. What matters for us to do the multiplication AM is that this guy here is the same as this guy. So the number of columns of the left factor must be the same as the number of rows of the right factor. So what do we expect? So AM, size of AM is equal to 2 by 2. Okay? So it's like these two guys here will be joined together and disappear, and then you have your 2 by 2. Okay? And now let us do the actual multiplication. So AM. So I'll try to use different colors. So let us start with the red. So the first one, I'm going to multiply this with this. Okay? So you will have 1 times 1. Let me write this completely. You have 1 times 1 plus 3 times 5. So 3 times 5. And then you have your negative 1 times negative 2. So plus negative 1 times negative 2. So that's the first entry in here. Okay? Now, let us multiply this guy here with this guy here. Okay? So you are multiplying this and then multiplying this. Okay? Now, let me emphasize this. So, where do you put the entry after multiplication? So look, you are looking at the first row. So for the red first, the red guys. So you are looking at the first row, first column. Okay, so row 1, column 1. So the entry will be in row 1, column 1. Okay? And then, so let me write that. So row 1, column 1. So row 1, column 1. So for the reds. Now, for the blues, you have row 1, column 2. So the blue here, row 1, and then here we are looking at column 2. So if you do the multiplication, it should be in row 1, first row, but this time column 2. Okay? Therefore, on this part here. Okay? Let us do that multiplication. You have 1. You have 1 times negative 2 plus 3 times negative 1. 3 times negative 1. And then you have plus negative 1 times positive 3. So plus negative 1 times positive 3. Okay? So again, first row, column 2. That's why we are in the first row and at column 2. In column 2. And that's where we will put the multiplication and addition, etc. Okay? Now, let us look at this next. Say you have, let me use this color. Now, I'm going to look at these guys here. So, this time I'm at row 2. And then, let me use row 1, column 1 in M. Okay? So, row 2, column 1. So, second row of A, first column of M. So, we must write the multiplication at the second row and first column. So, this part here. Okay? So, you have 5 times 1. 5 times 1 plus you have 2 times 5. 2 times 5 plus then you have 3 times negative 2. 3 times negative 2. So that's your row 2, column 1. So second row, first column. Row 2 in A. And then column 1 in M. Okay. And then let's use this color. Now let us do row 2 in A. So row 2 in A. And then column 2 in M. So row 2 in A, column 2 in M. So now, the product, you will write that in row 2 in AM and then column 2 in AM. So you will have 5 times negative 2. So 5 times negative 2 plus 2 times negative 1, 2 times negative 1 plus 3 times 3. 3 times 3. And then you may now close this matrix. Okay? Okay? And then you do the addition, the multiplication and addition. So let me write, again, I'll just do this step by step. You have 1 times 1, that's 1, plus 3 times 5, that's 15. And then plus negative 1 times negative 2, that's positive 2. And then in this guy here, you have 1 times negative 2, that's negative 2. And here you have 3 times negative 1, that's minus 3. And then here negative 1 times 3, that's minus 3 again. Okay? And then let us look at this guy here. You have 5 times negative 2, that's negative 10. 2 times negative 1, that's minus 2. 3 times 3, that's plus 9. And then this guy here, for this guy here, you have, 5 times 1, that's 5. 2 times 5, that's 10. 2 times 5, that's 10. 3 times negative 2, that's minus 6. So, minus 6. Okay? Then again, let us close this. And let us write now the actual entries. So, 1 plus 15 plus 2, that's 18. So, that's your 18. In here, you have minus 2, minus 3, minus 3. That's minus 8. Please check my arithmetic. Then here you have 5 plus 10 minus 6. That's positive 9. And then in here, you have minus 10 minus 2 plus 9. That's minus 3. So this is your product AM. Okay? Product AM. Question on this? Okay? Okay, so let us work on the next example. Yes, question?
So is the size of your final one always going to be the number of rows times the number of columns?
Yes.
Okay.
So number of row in the left factor by the number of column of the right factor.
Okay, perfect. Yeah. Thank you.
You're welcome. Okay. Next question in here. BM. So A and B are the same, have the same sizes. So again, if we study that, so this is 2 by 3. There are 2 rows and 3 columns, and M, it's our previous M, it's 3 by 2. 3 rows, 2 columns, so the size for PM will be 2 by 2 again. Okay? And then, again, let us do that complete detailed version. So, here, first row, first column. Okay? So, let me do this again here. First row, first column. You have -1 times 1, -1 times 1, plus 2 times 5, plus 2 times 5, plus +1 times -2, so 1 times -2. So that's your first column, first row, first column. And then first row, second column, first row, second column. So the product will be on the first row, second column in here. You have -1 times -2 plus 2 times -1, 2 times -1 plus 1 times 3. So 1 times 3. Right? Next, you have second row, first column. Second row, first column. So 2 times 1, 2 times 1 plus 3 times 5 plus -3 times -2. So -3 times -2. And then finally, you have the second row here and then second column. So you have 2 times -2, 2 times -2, 3 times -1, plus 3 times -1, and then -3 times 3. So plus -3 times 3. Okay? And then as usual, let us write all those things. You have -1 plus 10 minus 2. Okay? And then here you have 2 minus 2 plus 3. Please check my arithmetic. And then in this guy here, you have -4 minus 3 minus 9. And then for this guy here, you have 2 plus 15 and then plus 6. Okay? And finally, let us write all the answers. I'll just use everything in red now. So you have minus 1 plus 10 minus 2, that's 7. In here you have you have 2 minus 2 plus 3, so that's 3. In here we have 2 plus 15 plus 6, this is 23. And then in here you have minus 4 minus 3 minus 9, that's minus 16. Okay, so if all my arithmetic are correct, then this is the matrix BM. Okay? Question. Okay? So, for you, I want you to work on this, a plus 3b times m of ours. So, I will skip this. But remember, we already did a plus 3b in the previous examples. In the previous example. Okay? So, you can just copy that and then multiply it to m. So let me go back to a plus 3b first. So this was your a plus 3b. Okay, so look at this, get this matrix, and then proceed with the multiplication for this part here. So copy that a plus 3b and then multiply it to m. And take note, a plus 3b will have size 2 by 3 also, because a and b have the same size and we were able to multiply a and b. Okay? Oh, sorry. We were able to multiply a times m and b times m. Okay? Question. Okay. So, some more remarks here. Two matrices can be added if they have the same size. So again, just emphasis on these matrices. Okay, two matrices can be added if they have the same size. Two matrices can be multiplied if the number of columns of the left factor is equal to the number of rows of the right factor. Okay? Now, a matrix can be partitioned or subdivided into smaller matrices or blocks. For example, you have this matrix A in here. We have a 3 by 3 matrix. So A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay? So we can partition this into the following. So we look at this matrix here or sub-matrix here, A11, A12, A21, A22. We also have this partition here, A13, A23. We have this partition here, A31, A32. And this partition here, A33. So this matrix A can be written as follows. So we label capital A sub 1, 1. So this is capital letter because it's a matrix. But the 1, 1 here tells you that it's on the first, so first entry, okay, in here, the first row and then first column of this new smaller matrix, okay? It looks like it is smaller, but it's actually the same matrix, capital A here. So your matrix A, capital A11, is the 2 by 2 matrix A11, A12, A21, A22. So that's the location here, and that's your A, capital A11 here. And then A12, so this guy here, it's your column vector, A13, A23. So this guy here. Okay? And then A21, it's the row vector A31, A32. So this guy here. Okay? That's your A21. And then your A22, capital A22, it's your small A33. So this guy here. Okay? So in essence, you have this guy here corresponding to this guy here. This guy here corresponding to this guy here. This guy here corresponding to this guy here. And then this guy here corresponding to this guy. Yes, question?
Yeah. Does that mean that eventually we'll be able to use matrices as vertically as much as horizontally?
Yeah. A lot of times, yes, we will be using vertical or those column vectors. Okay? Later in the course, we'll be using those column vectors. Okay? And then, much later, a lot of times I will be writing row vectors. Okay? So, I don't know which one will be used more often than the other, but yeah.
Okay, but both are usable, right?
Yes, both are usable. Okay? Other question. So again, this is just for partition, and possibly later in the course we will be using this partition matrix, and sometimes it works really well when we have partitioned the matrix. When we have partitioned the matrix and then operate on this partition matrix. Okay. So the matrices A11, A12, A21, A22, the capital letters A, we call them submatrices of your capital A. So sometimes you are just interested in this matrix, so let's get that matrix only. Okay? Or sometimes you are just interested in this submatrix, so let us label that submatrix. Okay? So we'll have some usage of that later in the course. And one way to use that is the following. So you have your matrix A. Okay? M by N matrix. A11, A12 until A1N, A21, A22 until A2N, etc. And then we write it by rows. So you have this row 1, A11, A12 until A1N, A21, A22 until A2N, etc. until AM1, AM2, AMN. So by rows. So this is row 1. That's your row 1 here. This is your row 2 until you have your row M. And take note, I am using small letter R with bold face. Okay? Or in bold. Okay? Because it's a row vector. So sometimes we'll just have to look at by row 1 here. Okay? We can also do columns. So instead of dividing or partitioning the matrix by row, let us partition it by column. So this is your first column, A11, A21 until AM1. Second column, A12, A22 until AM2, etc. So this small C1, bold face C, take note. So it's your column 1, bold face C2, column 2, until you have bold face CN, column N. Okay? So how do we use this? So here, suppose A has m rows, okay? And then B has n columns, okay? So A has m rows, so A1 here, A2 here, until AM here. B has B columns, so column 1, column 2, until column n. And we assume that the number of columns of A, because it cannot be seen here, okay, cannot be seen here, the number of columns of A equals the number of rows in B, or of B, okay? The number of columns of B cannot be seen here. What you can see for capital B in this form is the number of columns, but the number of rows cannot be seen. But let us assume they are equal to R. So number of columns of A equals R, number of rows of B equals R. So what do we have? A, size of A. So let me just write it this way, size of A. This will be what? So M rows by R columns, correct? And then for the size of B, B has R rows, so you have R, and then number of columns, okay, you have N. Which means, look at this and this. What we can do is multiply. So this gives us product AB. That's possible, okay? And the size of this will be equal to M by N. Okay? So we can multiply this. Okay? But how will it look like? You have AB. Okay? So your A times that B here. Okay? Times that B here. Okay? So you can, it looks like we can distribute the A to each of the column of B. Okay? And another way of looking at it, so your AB, still your AB, this time we wrote this vector for A, this representation for A, and B is still on the right side. Okay? So again, here A is on the left side, A is on the left side, A is on the left side of B. Here you have AB, so B is still on the right side, so B is on the right side of A. And in this form, it looks like we are distributing your B. And B remains on the right side in this form. Here on this form, A remains on the left side. Okay? And when you do this way, you will still get your M by N matrix after simplification. Okay? So just another way of multiplying matrices using partition. Okay? So for example, let us use the same example as in before, but this time let us do this. Do this way. So you have your A, and then your M. Okay, your M, it's this guy. So this is your small m, 1, and then this is your small m2. Okay? So what is your AM? So AM is something like this. So AM is something like this. You have your A, M1, and then here you have your A, M2. Okay? In partition form. So here, you will have what? Your A, let us write that matrix. 1, 3, -1, and then 5, 2, 3. And then your M1, your first column for M, it's 1, 5, 2. 1, 5, 2. And then for the other guy, AM2, you have again 1, 3, -1, 5, 2, 3. 5, 2, 3. And then your M2, it's -2, -1, +3. Okay? So this is like looking at the multiplication in the easier way. Because in here, you have your column 1 and then column 2, and then you have, you have your row 1 and row 2, and then you just have one column to multiply. In here, you have row 1, row 2, and one column to multiply. So you are like separating them. Okay? And in this manner, so this guy here, it's in the first column. This guy here is in the second column. But looking at A, so row 1, row 2. So you still do that. So this guy multiplied to this for row 1. And then here, this guy multiplied to this for row 2. So it's still the same. So 1 times 1 plus 3 times 5 plus -1 times 2. Okay, so this guy multiplied to this guy. And then in here, you have 5 times 1 plus 2 times 5 plus 3 times 2. Okay, so this guy multiplied to this guy. And then the same way on the other side here. So you have 1 times -2 plus 3 times -1, and then plus -1 times 3. So this guy here multiplied to this guy, and then this here multiplied to this. So you have your 5 times -1, 5 times -2 plus 2 times -1 plus 3 times 3. Okay? And then you still get the same answer as in before. Okay? So somehow, things are simpler because in a sense, you know which column you are multiplying with, the row of the left factor. Okay? In this particular form. So you can do this. You can continue with the solution for this part. Okay? And then, let us look at the next one. BM. So this time, we write B in row forms. Okay, row form. So row 1, row 2 until row M. So if you multiply this with M, you will get this. BM, B2M, B1M, B2M, etc. BMM. Okay? So the same thing. This time, it is your M that you are multiplying to the left. Okay? So this is your row 1 here, multiplied to M. then row 2 here multiplied to m. So what you will see in this form would be, so row 1 here, you have your negative 1, 2, 1 multiplied to m. So multiplied to m, it's 1, negative 2, 5, negative 1, negative 2, 3. Okay? And then row 2 for B, you have 2, 3, negative 3. Then multiplied to m. You have 1, negative 2, 5, negative 1, negative 2, 3. Then you have this. Then again, it looks much easier because you are only multiplying a single row to this guy here. So this multiplied to this will be on the first column. This multiplied to this will be on the second column. And then in here, the second row of B multiplied to this will be on the first column. This multiplied to this will be on the second column. And then you should get the same answer as in before if you do the multiplication. Okay? So, question.
Could you please show the previous page for a second?
Yeah. This guy here.
Thank you.
Okay, you're welcome. So with the method of multiplication earlier discussed, let's have the following theorem. Let A be an m by n matrix and let x be an n by 1 column vector. So our A is represented this way. So A11, A12 until A1n, A21, A22 until A2n, etc. until we have AM1, AM2 until AMN. And then X is a column vector. So entries are like this, X1, X2 until Xn. Okay? So if we multiply A times X, okay, so A times X, then we will have the following. So AX, okay, equals A11, we have the first column of A multiplied to the first entry of X, okay, and then we have the second column of A multiplied to the second entry of X until we have the last column of A multiplied to the last entry of X. Okay, so how do we see this? How do we see this? Let us start with the following. So this is our matrix A. This is our matrix A, and this is the column vector X. So remember, when we do multiplication, we multiply row and then the column. So we multiply the row of the left factor with the column of the right factor. But we only have one column in here. So each of the row here in A will be multiplied to the column vector in A. Okay? So if we do that multiplication, here's what we're gonna get. So A11, A12 until A1n. So this row here being multiplied to this column. So A11 times X1. Okay? So you have your A11 here multiplied to X1 plus A12 here multiplied to X2 plus A1 in here multiplied to Xn. That's your first row. A11 X1 plus A12 X2 plus until A1n Xn. And then similarly, so let me label this blue part here. Then similarly, you have your A21 multiplied to x1, A22 multiplied to x2, and then until A2n multiplied to xn. So that's your second row in here. Okay? And then you continue the process. You have your AM1 multiplied to x1, AM2 multiplied to x2 until you have your AMN multiplied to xn. So that's your last entry here. And notice, this is just a single number because you are multiplying A11 x1. So A11 is a number. If x1 is a number, then this is just a number. And then you add those numbers. So basically, this is a column vector. This is a number, this is a number, and this is a number, and you only have a column. Okay? You only have a column. Now, what we're going to do is to apply the linear combination thing or linear combination concept. Okay? So if we do that, this is what we will get. So you separate this. So look at this. You separate this first part here, and then you separate it from these guys here, separate from these guys here, and you separate these guys here, so that you will have this expression. So notice, you have a column vector, column vector, column vector. They have all the same number of entries. You are just adding matrices, correct? And when you are adding matrices, you must have the same size. So they have all the same size. And you just add entry-wise. Correct? So in here, you have A11 x1 plus A12 x2 plus until you have A1n xn. And then on the second entries, A21 x1 plus A22 x2 plus until you have your A2n xn. So let me go back to this slide. So you have that, the red guys, for the second entries. Okay? Now, look at this. For this column vector, you have all x1. Okay? For this column vector, you have all x2. Until the last part here. For this column vector, you have all xn. And remember scalar multiplication. When you have scalar multiplication, you multiply the scalar to all the entries in the matrix. So you can think of this x1 as the scalar for this column vector. Here, x2 is the scalar for this column vector. Until here, you have xn for this column vector. So you can bring it out of the matrix and get these guys here. Okay? So A11, A21 until AM1 multiplied to x1, A12, A22, AM2 multiplied to x2 until you have this A1n, A2n, AMn multiplied to xn. Okay? So it looks easy in the computation process. Why? Because let us go back to this theorem. So you have the matrix A. You only need to do multiplication of this column with this entry. So first column multiply to the first entry. Second column multiply to the second entry until you have your last column multiply to the last entry. And then you will all have column vectors. You just add them. Okay? So one of the applications of partitioning. Okay? Now, let's have some more. For example, you have written A in terms of column vectors. So A1 is a column, A2 is a column, until AR is a column. And then your B, it's a row vector. So B1 is a row, B2 is a row, BR is a row. So A is in terms of columns, B is in terms of rows. Okay? So if you multiply AB, okay, you multiply AB, what you're actually doing is multiply the column for A to the row of B. And it's like entry-wise multiplication. So AB, so A is equal to A1, B1. So first column of A multiplied to first row of B plus second column of A multiplied to the second row of B plus until the last column of A multiplied to the last row of B. And we call this the column row expansion of A, B. Okay? Question so far? So again, these are just some other ways of multiplying matrices. But a lot of times, okay, a lot of times students just do the definition, the very first, the definition of multiplication of matrices. Okay, so these are just possibly easier ways when you are dealing with general matrices, like you just have A11, A12, etc., etc. Okay, but it could be also helpful in the particular cases. But as I have said, most students will just do the definition. It could be longer, but at least they are sure that that's the way to do it. Okay? Question? Now, let us go back to linear systems. Okay? So let us consider the linear system A11x1 plus A12x2 until A1n xn equals B1. That's your first equation. Here you have A21 x1 plus A22 x2 plus until A2n xn equals B2, second equation, until you have this last equation. Okay? So what we're going to do is to convert this to the following. So let A, okay, be the entries, be the matrix whose entries are the coefficients of your variables x1, x2 until xn. So look at that numbering. So A11, A12, A1n. Okay? A11, A12 until A1n, A21, A22 until A2n. So you have that. So this is like your augmented matrix. But this will have a name. I will give you the name now. The name is actually matrix of coefficients because these are all the coefficients. Okay, so matrix of coefficients. And then the unknown variables, x1, x2 until xn, we put it as a column vector. So look at how we wrote that. Okay, x1, x2 until xn is a column vector. And then these constants, okay, the constant parts of the equation, so b1, b2 until bm, we write it also as a column. But notice, x1 has n entries, b has m entries. So this b still tells you the number of equations you have. So the number of entries in your column vector b is the number of equations you have. Okay? So we will convert that to another form. So from now, you have your matrix A, column vector X, column vector B. Okay? We can now write this linear system in the following. manner or in the following form. So AX equals B. So we call this the matrix equation of the linear system. Okay? And as I have said, the matrix A is called the coefficient matrix or the matrix of coefficients because you only see the coefficients of the variables. And notice, this makes sense because you see, you have n columns for A and then you have n rows for X. And multiplication makes sense. So this row here multiplied to each of this. Okay, and there's an equality there. So this row here, so row 1 multiplied to the X equals the first entry of B. That's your first equation. Row 2 multiplied to the X equals the second entry for B. That's your second equation, and etc. etc. Okay? Now, let us look at some of these definitions. Let A and B be M by N matrix. Okay? So these are an additional additional operators for the matrices. Okay? So let A be an M by N matrix. The transpose of A, denoted by A with the superscript capital T, okay, is the N by M matrix with these entries. So A transpose Aij equals the Aji of the matrix A. So that is the Ij entry of A transpose is the Ji entry of A. Okay? So look at this. The size of capital A, it's M by N. Now, the size of A transpose, it becomes N by M. Okay? So what actually happens here? The rows of A become the columns of A transpose. Okay? For example, we have here A, M, and C. So A, it's 2 by 4. Okay, 2 by 4 matrix. So if we look at A transpose, so the rows of A becomes the columns or become the columns of A transpose. So for the row 1 here, it will be written as the first column of A transpose. So this one is A11, A12, A13, A14. And then in here, the second row of A becomes the second column of A transpose. A21, A22, A23, and A24. Okay? Now, do not be confused with the labeling of entries in here. It's just that we are looking at these entries. Okay? We are just looking at the entries of A, and the labeling also should follow the entries of A to get your A transpose. But in essence, rows become columns of the transpose. So for M transpose, let us look at that. For M transpose, so you have your 2 or 3 by 2 matrix for M. Okay? So rows become columns. So you have 1, -2. That's your first row for M, and the transpose becomes the first column. Second row of M, you have 5, -1. And then the third row of M, you have -2 and +3. Okay? So rows become columns. And you have your C transpose. So your C, it's a column vector. When you get the transpose of that, it becomes row vector. So it becomes 1, 2, negative 2. Okay? 1, 2, negative 2. Question? For the transpose. It's an easy operator. Next operator here. Let A be a square matrix. Take note of that condition. A square matrix meaning number of rows equal the number of columns. Okay? Now we will consider what we call the trace of A. So denoted by this TR and then A. So trace of A. So this is the sum of the entries in the main diagonal of A. So remember your main diagonal? So if you have the square matrix, the main diagonals are the entries at the II position, meaning A11, A22, A33, A44. So those are the entries in your main diagonal. Okay? So you look at that, you get all the entries, you add them. And that becomes the trace of the matrix A. For example, in here, you have the trace of A. So this is a 4 by 4 matrix. Okay? And the main diagonal in this 4 by 4 matrix, you have this. Right? So you just need to add that to get the trace. Okay? So trace of A, this is equal to A11 plus A22 plus A33 plus A44. Okay? Then we look at trace of B. So for the trace of B, again, the main diagonal is this guy here. So you just add those entries. You will have 1 plus negative 1 equals 0. Okay? And then in here, you are asked to find trace of B transpose. So let us look at B transpose. So as I have said, rows become columns. So row 1 in here, you have 1, negative 2. And then row 2 in here, 5, negative 1. And the main diagonal is this guy here. Okay? And you will see that the trace of B transpose, this is 1 plus negative 1, and again this is equal to 0. Okay? Now, at this point, let me give a particular remark. When you have a square matrix, okay? When you have a square matrix, and you try to find the transpose of that, the main diagonal does not change. Right? Because again, in the transpose, the Aij entry of the matrix A becomes the Aj entry of the A transpose. But you have your main diagonal entries. And what is the representation of the main diagonal entries? it's the same row and the same column. So II, okay? Or JJ if you want. And therefore, it won't change. AJJ is still AJJ in the transpose. Okay? So you will see later that the trace of your matrix B is the same as the trace of the matrix B transpose. Okay? Provided, of course, again, the condition to get the trace, the matrix must be square. Okay? Question so far? Let us work on these examples. So you have CT transpose, also C transpose A transpose plus 2E transpose, and then you want to add, you want to get the trace of that. Okay? So let us first work on the C transpose and the A transpose, and also your E transpose. So let us do this step by step. First, C transpose. So you have this, okay? Rows become columns. So you have 1, 4, 2. And then you have 3, 1, 5 on the second column. And then you also want your A transpose. A transpose in here. So you will have, so rows become columns. The same way, columns become rows. So you have here 3. So this is your first column. So it becomes the first row of A transpose. So 3, negative 1, 1, 0, 2, 1. Okay? And then we need C transpose, A transpose. So will that make sense? So C transpose, A transpose. So your C transpose size is 3 by 2. So 3 rows, 2 columns. And then for the A transpose, you have 2 rows by 3 columns. So 3 by 2, 2 by 3. So the size of C transpose, A transpose will be 3 by 3. Okay? So anyway, you have C transpose, so 1, 4, 2, 3, 1, 5. So work with me. So while I write the solution in here, also try to write independently your solution, and let us compare the answers. Okay? So first, so we will have a 3 by 3 matrix in here. So here you have 1, 3 multiplied to 3, 0. So 1, so 1 times 3. So 1 times 3. Then 3 times 0. So plus 3 times 0. And then 1, 3 multiplied to negative 1, 2. So 1 times negative 1. 1 times negative 1. 3 times 2. So plus 3 times 2. And then your 1, 3 multiplied to 1, 1. So first row multiplied to third column. So you have 1, 1. 1 times 1 plus 3 times 1. 3 times 1. So that's your first row. Second row. Second row. We have 4 times 3. So 4 times 3 plus 1 times 0. And then 4, 1 times negative 1, 2. So 4 times negative 1 plus 1 times 2. And then you have 4, 1, and then 1, 1 in here. So 4 times 1 plus 1 times 1. And then for the last row, 2, 5 multiplied to 3, 0. So 2 times 3 plus 5 times 0. And then 2, 5 multiplied to negative 1, 2. So 2 times negative 1 times 5 times 2. Plus 5 times 2. And then 2, 5 multiplied to 1, 1. So 2 times 1 plus 5 times 1. So just a quick observation. If you are multiplying with the correct column, if you write it this way, look at this. So you have 3, 3, 3, 0, 0, 0. Negative 1, negative 1, negative 1, 2, 2, 2. 1, 1, 1, 1, 1, 1. So you will observe that. Okay? And of course, if you are multiplying with the correct row, you should see that 1, 3. So 1, 3, 1, 3, 1, 3. You have your 4, 1 here. You have 4, 1, 4, 1, 4, 1. So consistency. Now let us write the entries. So 1 times 3 plus 3 times 0, that's just 3. You can simplify immediately. Then 1 times negative 1 plus 3 times 2. So negative 1 plus 6, that's 5. Here you have 1 times 1 plus 3 times 1. So 1 plus 3, that's 4. Here you have 4 times 3 plus 1 times 0. So that's 12. Here 4 times negative 1 plus 1 times 2. That's negative 2. Kindly check my arithmetic here. And then here you have 4 times 1 plus 1 times 1. You have 5. Here you have 2 times 3 plus 0 this part. So you have 6. Here 2 times negative 1 plus 5 times 2. That's 8. And then here you have 2 times 1 plus 5 times 1. 7. Okay? So this is your C transpose, A transpose. Now, let us write 2E transpose. So 2E transpose. So you will have 2 times E transpose. So rows become columns. So 6, 1, 3. Negative 1, 1, 2. 4, 1, 3. 4, 1, 3. Okay? Then multiply that 2. So you have 2 times 6, that's 12. 2 times negative 1, that's negative 2. 2 times 4, that's 8. So I will need a little space in here. Let me write this in smaller. So 12, negative 2, and then 8. And then you have 2, 2, 2. And then you have 6, 4, 6. So this is the matrix. Okay? And then you can add them. If you add them, let us copy this. Let us copy this part here. Then let us use another slide. this guy here. Let us copy again. I hope it can be copied. Yeah, so this is your, so you have the plus in here. So this is the C transpose A, C transpose A transpose plus 2E transpose. So this is what you have in here. Okay? So if we add that, you can add everything. You have 3 plus 12, that's 15. So that's the first entry. 5 times negative 2. 5 plus negative 2, that's your positive 3. 4 plus 8, that's 12. Then 12 plus 2, that's 14. Negative 2 plus 2, that's 0. 5 plus 2, that's 7. 6 plus 6, that's 12. 8 plus 4, that's 12 again. 7 plus 6, that's 13. Okay? So this is the sum. C transpose A transpose plus 2E transpose. And then finally, we look at the trace. So for the trace, you just need this main diagonal here. That's your main diagonal. So you will only have 15 plus 13, which is equal to 28. So that's the trace of the matrix. Okay? So it has long solution because you see, you need to do C transpose, A transpose, you have to multiply them. You also have your A transpose and then multiply it to 2. And then you add the two matrices, okay, before getting to the trace itself. Okay? What else? Some students skip a lot of steps. Okay? Sometimes I accept that, especially when we for example, for this case here, I only want the trace of this guy here. Okay, I only want the trace of this guy here. So if we go back, let us go back to the previous slide. So since I only want the trace of this sum here, what students do is just to compute the entries in the main diagonal. Okay? For example, you have to get your C transpose A transpose. That's a definite. That's a necessary step. And then here, you need to multiply C transpose A transpose. So you have to write this. But what students do, since at the end they just need a trace, they only compute for the entries in the main diagonal. You will know that the A11 entry, it means you multiply first row, first column. A22 entry, multiply the second row, second column. A33 entry, multiply the third row, third column. So those are just your main diagonals. The entries in the main diagonal, I mean. And then they skip this part here. Similarly for this. Okay, similarly for this. They can easily see that 2E transpose, the main diagonal will just be this part here. Okay? And then they add the main diagonals. Because in the end, we only need the main diagonal. Okay? And addition is entry-wise. So, when they add that, when they add the two matrices, what they only have are the main diagonals. So they only need to add the main diagonals. So they will only have this. And then compute for the trace. Add the entries in the main diagonal. So that's what some students do. So sometimes it's acceptable. Okay? But there are times where I actually look for the trace, the C transpose first, A transpose first, or multiply C transpose A transpose, etc. So sometimes I divide this into several parts. Okay? So the solution will lead to the trace. So sometimes I look for what I ask is find C transpose and A transpose. Then find the product C transpose A transpose. So that's what happened in here. We find C transpose A transpose. Then we find the product, this C transpose A transpose. And then a second part of that is find the sum, C transpose A transpose plus 2E transpose. So they will skip this part. They already got this. Okay? And then, no, they will not skip this part. They already have this and then combine it with this. Okay? To have this part here. And then the last question probably find the trace. And that's the time you have this. Okay? Because when I do that in one set of questions, what do I check? I check if you know how to get the transpose. I check if you know how to multiply matrices. I check if you know how to do scalar multiplication. I check if you know how to add matrices. And finally, I check if you know how to get the trace. So all the operators in one single question. Okay? All the operators I want to see whether you know or not in a single in a single problem. Okay? But a lot of students skip many things. So sometimes I give deduction because they don't write the actual multiplication or so, and they got wrong uh, wrong value, so they will get bigger deduction as compared to they have the actual solution. I know or I see that they know how to do multiplication matrix. It's just that they miscalculate something. Okay, so that miscalculation will only get smaller deduction. So it really depends on what will happen. Okay, but for now, try to practice to do everything. So it practice your matrix multiplication. It practice your transpose of matrices, etc. Okay? I hope that is clear. Now, another example here. So you have matrix A and then matrix B. Okay? Matrix A and then matrix B. So both are 3 by 3 matrices. So here, I want to find the first row of AB. Okay? Just the first row. You don't have to calculate everything. So what does this mean? If you want the first row of AB, you just need to consider the first row of A multiply to all the columns of B. Remember, when doing multiplication of matrices, the left factor, you use rows. The right factor, you use columns. Yes? Okay. So we need the first row of AB, so we just consider first row of A and then multiply it to the columns of B. For the second problem here, we want the second column of AB. So this time, we want the second column, which means I need to work on the second column of B and multiply it to the rows of A. So all the rows of A multiply to the second column of B. And that you will get the second column of AB. So here, let us write that. So for number 1, so you have your AB, and we only need the first row. So first row. First row. So row 1 multiplied to all the columns of B. Okay? So first row, first column, you have 3 times 6. 3 times 6 plus negative 2 times 0. So negative 2 times 0 plus 7 times 7. So plus 7 times 7. So that's your first row, first column entry. Now, first row, second column entry, you have 3 times negative 2. So 3 times negative 2, negative 2 times 1. So plus negative 2 times 1. And then 7 times 7 plus 7 times 7. So that's the second entry in the first row. Okay? And then first row, third column. So you will have 3 times 4 plus negative 2 times 1. Times 3. Times 3 plus 7 times 5. Okay? So you have that big matrix, but you are only interested in the first column. Okay? So anyway, let us just simplify this. The first row. So in here, first row. Let me just write this. First row. First row, you have 18 plus 0 plus 49. So 18 plus 49. Then here you have negative 6 plus negative 2. So minus 2. And then plus 49. Then lastly, you have here 12. 12 plus or minus 6. Minus 6 and then plus 35. And then we simplify this. So what are the numbers? So 18 plus 49, that's 67. And then in here, minus 6 minus 2 plus 49, that's 41. And then in here you have 12 minus 6 plus 35, that's 41 again. Please check my arithmetic there. So this is the first row of AB. Okay? Okay? Let us work on the second problem here. So the second problem, you have AB, but let us just look at the second column in here. Second column. So for the second column, this should be a column vector because second column. But that means you are gonna multiply each of the row from A to the second column of B. Okay? So here, first row, multiply to the second column. So you will have 3 times negative 2. We already had this in the first problem. And then negative 2 times 1. To 2 times 1. And then 7 times 7. So plus 7 times 7. So that's first row, second column. Second row, second column. So you have 6 times negative 2. 5 times 1. So plus 5 times 1. Plus 4 times 7. Then lastly, third row times second column. So 0 times negative 2. Plus 4 times 1. Plus 9 times 7. So simplifying, oops, don't have enough space there. So if we simplify this, what do we have? 3 times negative 2, that's negative 6, minus 2, plus 49. For the second entry, you have minus 12, plus 5, plus 28. Third entry, you have 0, plus 4, plus 63. So plus, so plus 63. So if we add them, what are we getting? So again, this is 41. So minus 6 minus 2, that's minus 8, plus 49, that's 41. Here you have minus 12 plus 5 plus 28. What is this? 33 minus 12? 21. Is that 21? And then you have 4 plus 63, that's 67. So this is the second column of the product A, B. Okay? Question. Okay? So the remaining slides here are exercises. Okay? So you have this first set of exercises, another set of exercises. So same problem, same questioning. Okay? Here you just have multiplication. Okay? And then in here you have similar problem to the last examples that we discussed. And then in here we have a situation, okay, and then we write it as a matrix, okay, or as a product of matrix. Okay, so try to interpret this, okay, with this information above here. Try to interpret it as a matrix, and the question is, what information is represented by the following product? Okay, so these exercises you can do it at home. But yeah, I still have 1 hour. So let us do some of the problems here. Let us look at this. I want to work on this product AB and then the product BA. Okay? I want to work on the product AB and then the product BA. And then we will show that you cannot just interchange the location of the matrices in the multiplication. Unlike in the set of real numbers, your 3 times 2, this is equal to 2 times 3. So you can interchange this, actual numbers. Okay? But in the matrices, if you multiply two matrices, A, B, it may not be the same as BA. In fact, in this particular set of matrices, okay, we will show that they are not equal. Let us do this. So let us start with AB. So AB, let us copy A. You have 3, 0, negative 1, 2, 1, 1. So again, try to work independently and then let us compare answers. B, it's 4, negative 1, and 2, 2. 2, 2. So notice, you have here 3 by 2, and then in here you have 2 by 2. Okay? 3 by 2, and then 2 by 2. So you expect a 3 by 2 matrix. 3 rows, 2 columns. So what do we get in this part? So first row, first column, 3 times 4, you can write immediately as 12, that as 12, and then 2, 0 times 2, that's 0. And then in here, negative 1 times 4, you can write this immediately as negative 4, 2 times 2 here, so plus 4. Then here, 1 times 4, that's 4, plus 2 times 2, plus 1 times 2, that's 2. So notice, I work on per row on the left matrix, and then just the first column of the right matrix. So I just have the first row, first column of the product. Now I work on rows and then the second columns. So 3 times negative 1, that's your negative 3. And then 0 again, 0 times 2, that's 0. The negative 1 times negative 1, that's 1. 2 times 2, that's 4. So plus 4. Then you have here 1 times negative 1, that's negative 1. 1 times 2, that's positive 2. Okay? And then this matrix is now equal to, so let us just simplify. So you have 12, and then 4 minus 4, that's 0. And then 4 plus 2, that's 6. Okay? And then this is negative 3 here. You have 1 plus 4, so that's 5. And then negative 1 plus 2, that's positive 1. So this is the product AB. That is the product AB. Okay? Let us look at BA. So BA. Size of B, it's 2 by 2. 2 by 2. Size of A, it's 3 by 2. So observe, this guy here and this guy here, they are not equal. Okay? Which means that this cannot happen. So this one cannot be. And therefore, AB is not equal to BA. So you cannot just interchange two matrices if you do multiplication. AB is not equal to BA in general. There are several matrices where you have AB equals BA. Okay? But it's not always the case. Okay? Question? Now, look at number 2 and number 4. So you have the brackets. So start with the brackets. Start with the brackets and then multiply the other matrix. Okay? But later we will see that if you are multiplying two matrices or three matrices, you can regroup this and the answer will be the same. Okay? So meaning, for example, in this particular problem, you have A times B first, multiply to the right the matrix C. Okay? But later we will see that this is also equal to A times B C. Meaning you multiply B and C first in that ordering, so B times C, and then you multiply to the left the matrix A. So meaning the ordering A, B, C will not change. But you can regroup A, B times C, or you have A times BC. So start multiplying BC first, then you multiply to the left A. In here, you multiply AB first, then multiply to the right C. So we will see later that this is true. Okay? By later, I mean in the next lecture. Okay? Now, for this, look at this. You have your matrices A and B. And let us do number 4. So look at the problem. The entry on the third row and second column of AB transpose. Okay? The third row and the second column of AB transpose. So let us work on this problem. So what we want is the AB transpose in here. Okay? And then you want the third row, second column. So you have the third row, second column. Okay? And remember, now, try to observe, okay, that this is the same as you just use the product AB. So you are removing the transpose. But what is the definition of the transpose? You interchange columns and rows. Okay? Columns and rows. So if you want AB transpose 3, 2, then you can just work on AB 2, 3. Okay? Okay? So what does this mean? You now have your AB. You now have your AB and you want the entry 2, 3. Meaning, you have to use second row of A, multiply it to the third column of B. And that will be the answer to problem 4. So if you want this, you want the second row of A. Second row of A, what is the second row of A? So 6, 5, 4. 6, 5, 4. Multiply it to the third column of B. So third column of B. 4, 3, 5. And if you do this, what will you get? Let me write the answer here. I need the space. Oops. So let me just write the answer on this part here. You have 6 times 4, so equals, so 24 plus 5, so 6 times 4, that's 24, 5 times 3, that's 15, plus 4 times 5, that's 20. So this is equal to 24 plus 15, that's 39, plus 20, that's 59. So that's the entry on the third row, second column of AB transpose. Okay? So you don't have to calculate the matrix, the product of the matrix, and then transpose it, and then find the entry. So you can immediately get which entry by this description. Entry on the third row, second column of AB transpose. Okay? And for this one, let us see. Suppose that type 1 items cost $1 each, type 2 items cost $2 each, and type 3 items cost $3 each. Also, suppose that the accompanying table, so this table here, describes the number of items of each type purchased during the first 4 months of the year. So January, February, March, April in here. Type 1, there are 3 items in January, 5 items in February, 2 items in March, 1 item in April. And then you have your type 2. You have 4 items in, so 4 units in January, 6 units in February, 9 in March, 1 in April. And then in the type 3, you have 3 in January, 0 in February, 4 in March, 7 in April. Okay? So what information is represented by the following product of matrices? So in here, you see you have 3, 4, 3, and that's your first row here. Here you have 5, 6, 0, and that's your second row here. 2, 9, 4, third row. 1, 1, 7, that's the fourth row. While this guy here, what are these 1, 2, 3? These are the cost for each type from type 1 to type 3 respectively. So type 1, okay, type 1, $1. Type 2, $2. Type 3, $3. So if you do multiply this, if you multiply the product, you would, or you should observe that. So for example, in the first row, you will have what? 3 times 1. So let me do that. So you have this guy here multiplied to this. So you have 3 times 1 plus 4 times 2 plus 3 times 3. Okay? So let us look at that first row only. So does it make sense in the problem? Type 1 costs $1. So 3 times 1. 3 items in type 1 multiplied to $1. 4 items in type 2. Type 2 costs $2 each. So 4 items times 2. So 4 times 2. In type 3, 3 items. Each costs $3. So you have 3 times 3 here. That's your 3 times 3. So what is this sum that you see here? 3, 1, 3 times 1 plus 4 times 2 plus 3 times 3. What is that sum? What does it represent? You can type in your answer in the chat room. Or you can just speak. Total price for January. Exactly. That's your total cost. Okay? That's the total cost for your January. So this first row represents all the number of items for January. Okay? Everything, type 1, type 2, and type 3. These numbers are the items you bought or whatever, or purchased in January. Then if you multiply this by 1, by 2, by 3, okay, you will have that row, okay, and that means that's the total cost for the January. So you have the second row multiplied to this vector here, you will have the total cost for February and also for March and April, etc. So that's what we have for this product here. Okay? For this product here. So each entry in the product represents the total cost for the month. Okay? So that's it for today's lecture. Try to work on the exercises. Okay? And thank you for staying. So I'll see you next meeting.